And to be occupying yourself very nicely. Shall I not disturb you? So what we are going to do in this lecture is the nearly free electron approximation. And if we'll have time, perhaps we'll do tight binding. As I said in the previous lecture, these are two edges of approaching this problem. At the end of the day, they give us the same physical answer, the same qualitative answer, and where we use each one depends on what we want to describe. So we're starting with a nearly free electron. Okay, so we assume that we have a very weak potential. And if I put in a very weak potential, no matter how weak it is, something happens. Why? Because if I didn't have this periodic potential, any translation is symmetric, right? At the point that I add this very weak potential, something changed. The symmetry was broken, no matter how weak this potential is. Actually, at the point that this potential goes to zero, we have a singularity. And a very cute example of a singularity that I've heard from Michael Berry, someone who did a lot of work in topological effects in waves and in quantum mechanics, is the following. Let's say you bite into an apple and you find half a worm. That's bad, right? But if you bite into this apple and you find a quarter of a worm, it's even worse, right? And take it to the limit. If you bite into an apple and find no worm, what is it?
Could be both.
Could be both, but at the point where you're going from some infinitesimal part of a worm to zero, something basically changed. So the same thing here. Once you put in, break the symmetry by no matter, when it doesn't matter how weak this potential is, something changed. Because you had a continuous symmetry and you broke it into a discrete symmetry. Okay, let's look into the problem of very weak potential. And at the first point, let's just look into the breaking of symmetry. Ignore anything else that happens. Okay, so what happens there? Basically, for a free electron, this was your dispersion relation, the connection between E and K. famous parabola. For a nearly free electron, or I'll shorten it to NFE, I have already a discrete symmetry R and an inverse lattice, which is in the game. And for any G, I get the same solution. Now let's look a bit more carefully at what does this mean. And I'll plot it for one dimension just because it's easier, but it's correct for any dimension. Okay, I still have this E versus K. Okay, but now I have special points. Let's call it 0, which was special previously. But I have also and so on and so forth. And if I plot all these solutions, I get here a series of parabolas. These are all the solutions of the energy. Right? Because I'm taking the potential to be essentially 0. There are parabolas, these are the solutions. Okay, first of all, looking at it and seeing that I have too many points. Right? On one parabola I have whatever number of points that I have. Think about K in a periodic boundary conditions. So it's going to all the multiplication of 2 pi n divided by L. And here I have another one, and another one, and another one. Just too many points. The number of quantum variables, of quantum numbers, should be constant. It shouldn't change because I put in a periodic potential. So what happened here? So we go back to the concept that we introduced in the beginning of the course, the first Brillouin zone. So, where would be the Brillouin zone in this one-dimensional plot?
First one?
The first one?
G equals 0.
The pi over a minus pi over a, pi over a.
For the other side, you put it too far. You put it on G1, shouldn't it be 0 and G1?
Here it's minus half G1, and here I put that G1 over 2.
Yeah, no, because the line.
Ah, I put the line incorrectly, correct. Okay. And within this region, within the first Brillouin zone, I have the correct number of points. Okay, so the solutions exist within the first Brillouin zone. So I'm telling myself I'm looking only on the first Brillouin zone. Okay. Parabola. Then I have the solutions from the second one. And then I have the solution coming in from the third one, and so on and so forth. Okay, these are the solutions that exist in the first Brillouin. Just look what's happening here and plotted them. Now you look on it and you say, sorry, that doesn't remind me anything from free electrons, right? Looks completely different. But wait a minute. I have a symmetry. K and K minus G is the same. So I can take this guy and move it by G1. And what will I get? Because moving this guy to here, G1, and moving this guy to here by G1 gives me this. Do the same here, but move it by 2 G1. Sorry, by, again, here, again, by G1. And then I'll move it by 2G1 on the next one, and so on and so forth. So basically, I folded into the first Brillouin zone the parabola. Right? I have all my sections of the parabola, but folded into the first Brillouin zone. So basically, when I'm taking the potential to 0, essentially it's like changing the coordinate system. I'm starting to map all the k's only on the first Brillouin zone. Physics didn't change at all. Okay, that's the first point. Now I stop treating this solution as essentially going to zero and say it's not zero, it's small. Okay. When do I have the largest influence of a perturbation?
Largest influence?
Yeah.
So the edge of it?
Yeah, but how do you call these edges?
The edge of the Berlin zone?
And the Fermi
And
zone.
degeneracy.
Degeneracy. At points of degeneracy.
Oh, last week. No, I was discussing all of that.
Exactly, that's a general property of physics. Interesting things happen at degeneracy. Why? Because once you have degeneracy, the smallest perturbation usually breaks it up, and breaking up is where things change drastically. Okay, so you can look on this plot and say, excuse me, I always have a degeneracy, right? I'm choosing some energy. Let's call it E0. And it's the same. I wanted to move it a bit. Go. Okay. I'll leave this dashed line for later. Okay. If I'm here, this and this and this and this and this, so on and so forth, are connected.
But you can tell in which parabola you are standing, right?
But still I can't say in which parabola I am. That's one way to see it. And the other way is basically just a moment. Okay, so first you can, in any one of these points, you can decide in which parabola you are. That's one thing. The second thing, if I'm thinking about the matrix elements there, what will be the matrix element of in the first order perturbation?
The potential inside the...
It will always be
The potential inside the eigenvalues of the non-perturbative Hamiltonian.
right? What are these eigenvalues?
The non-perturbable.
Free electron. So it will be
Conjugate. K1 plus G.
right. If so, you have here basically a Fourier transform in Rx. And the Fourier transform of a periodic potential is non-zero only if K1 minus K2 is G. So for these guys, if I'm looking on two degenerate point, it's not G. The only point where it's exactly G is on these points where I have a crossing or a distance of G between these parabolas. So I have here, I'll have one here if I would have plotted it correctly, and so on.
And then also we can simplify the...
So if I'm looking on this guy, this point is degenerate, this point is degenerate, this point is degenerate, this point is also degenerate, but they are not coupled by a potential. So I don't care about the degeneracy. So something catastrophically or a big change will happen only on these points. Okay? And what happens in a degeneracy? Two or more values that were the same split, or at least potentially split. What does it mean in this plot? Basically,
Create a gap between them.
you will open a gap between them. So these points become gap, and I have an allowed band. I have a region of energies that have a value, and regions of energy where I can't be. So that's the whole idea between opening up gaps due to a weak potential. And now we'll do the mathematics as in an ordered fashion, but at the end of the day, this is all that stands there. This is all you really need to understand about it. Questions? Okay. If you remember, in the previous lecture, I wrote down the Schrödinger equation for a periodic potential as a Fourier transform. So I'll use it. So let's just define notation. Okay, from where does it come? Well, we did it last lecture, but we can also look on, does it make sense in physical terms? What do we have here? Let's assume we have no potential. Then it basically tells me that this side is equal 0, and this side is equal 0 either I'm at a different energy, or I'm sitting with this CK on the same point. So that's just this solution. The only point that I can have the energy is the point where I have this solution, a non-zero C. Okay, so it makes sense. What does the right hand say? Tells me, well, if I want to know what happens at a certain value of C, I have to know what is the coupling to all other values. And when do I have couplings? Only at distances of G, just because of the form of the periodic potential. Okay, I want to find what are all the other CKs minus G. Well, they have to fulfill there's nothing special with G1. Okay, someone can tell me what I did here?
You just
Just
divided.
move the terms around.
Right, I just divided by this guy. Okay, let's look what's happening here. Okay, I just rewrote this by dividing by E minus E0 K minus G. And now I'm going to insert it into here. Until now I didn't use the fact that I'm treating a small perturbation. Okay, but now I'll start using it. So I'm just copying the left hand here. G1. And now I'll just insert this value here. Now, where will I use the fact that I'm treating a small perturbation?
You're only going to work with nearest neighbors.
Well, I don't have here defined nearest neighbors, right? I'm in k-space. But what happens here? I have here one power of u, and here I will have higher powers of u just because I'll have to insert again this this behavior of ck. I'll have another power. So I'm taking only the first one, which is equivalent to what you have seen second order perturbation theory. So again, I'm just copying what's written here. And now writing the first term here. Okay. Is this in the summation?
No.
No.
It's not changed variables.
Can get rid of it. y absolute value squared, because I had g minus g1, and its complex conjugate. Okay, that's the form of second order perturbation. What happened to first order perturbation? Yes, why? It's self-evident that it's zero because it doesn't appear here. To remind you, in the previous lecture, we defined it that the average of u is equal 0. So the first, what will be the first order perturbation here? U0, right? But we defined it as 0, so it doesn't appear here. So all is good as long as this doesn't cancel out this and we have degeneracy. So the pictures that I have drawn before, as long as I don't have degeneracy, I'll have some movement in the energy, but nothing catastrophically. I have some second order perturbation, which is usually small, certainly for a small potential. Things are not good at the point where this can be equal to this. And where that can happen, we already know. At either zeros or edges of the Brillouin zone. There I have to be careful. Okay, so in principle, if I'm treating like a two-dimensional or a three-dimensional system, it can have a whole line or a whole surface of degeneracies. But let's keep it simple. Let's assume we are considering only a double degeneracy, which in one-dimensional always happens. So what happens in a double degeneracy? We have to stop and go back to the original Hamiltonian, but treat careful is the point of degeneracy. Okay, I wrote the components of C at the points of degeneracy G1 and G2. And I have to worry about it only if this term is not equal to 0, meaning that the difference between G1 and only happens between G1 and G2, which are both reciprocal vectors. Okay, let me perform here a change of variables. I'm always allowed to do that. So rewriting these equations. Let's rewrote the first one. Always couples between the opposite ones. Okay. How do I solve it? Well, these twos, I transfer it to the second side and I get 0. When is it 0? Basic linear algebra.
And the determinant?
When the determinant is 0. Okay, so if you don't see it, I'll write it down explicitly. Just a solution, the determinant describing this equation. So, just writing down explicitly this determinant. But sorry. So what is the size of the gap?
So, 2G, like the absolute.
2 UG. So if it's very small, you hardly see the gap. If it's larger, can have a significant influence. Okay, another interesting thing. So we have a gap. How does the wave function at the region of the gap look like? At the values where you open the gap, at the degeneracy?
0.
The wave function is not 0. So for such a solution, what is usually the solution?
It's a linear combination of the undisturbed.
Right, it's plus and minus for these undisturbed values. So, in general, and here I'm writing it down for any dimension, because it's still... This way. Just from the point that it's a linear combination of either plus or minus the degeneracy point, at the degeneracy point. What does that tell us about the wave function? We started with solutions that were I to the power I k dot r. And we ended up with solutions that remind us a standing wave. We started from an expanding wave and ended up with a standing wave. So at the highest and lowest point of the band, our wave is hardly propagating. It's the furthest from a free electron that we would have can get in the system. So although it's a linear combination of propagating waves, it itself doesn't propagate. Its group velocity is almost zero, or exactly zero at the degeneracy. So what does that tell us? Tells us that if we are looking at the ability of a state to carry current in the system, it's the lowest at the edges of the band. Okay? If you want to see a propagating wave, you have to move more and more into the middle of the band. Okay, so now we're at exactly the point where we can understand, at least very generally, when are we a good conductor, a metal, and when are we an insulator. So I'll draw it for 1 dimension, but after we'll do tight binding, I'll also look at higher dimensions. Is it just this way? Okay, we have K. We have our first Brillouin zone. Started with these solutions. We corrected for the degeneracy, and we ignore second order corrections. Okay. How many points do I have on the first curve, on the black curve? If I'm assuming I have a finite number of atoms and I'm doing periodic boundary conditions. Have here n atoms, periodic boundary conditions.
2n?
Well, the answer is n if I don't take spin into account, 2n if I take spin into account. So I have here n points, n states, if you want. Here I have and if I take into account spin, I have 2. Now let's assume I have 1 free electron per atom. These are my atoms. Where will be the Fermi energy?
The first.
Exactly after I fill up n states. So, the electron pair atom. That's not close to a degeneracy point, not at the edges of the band. The wave function are nice propagating waves. I put in some small voltage to carry current. I'll lose some of the left-going states. I'll move them to right or vice versa, depends on the direction of the field. And I'll have a nice current going through this. So it's a metal. Let's say I have 2 free electrons per state. So I need to fill up all these guys. The Fermi energy is in the gap. I'm stuck at states that can't carry current, both because their behavior is stationary states, and if I put in a small amount of energy, they can't move from their filling because there is a gap. So that's
But if you make some large enough potential, you could move them, right?
yes. And now 2 caveats. Well, here I've plotted the 1-dimensional case. For a 2-dimensional case, I'll have the Brillouin zone is an area. For 3-dimensional, it's volume. So we have to take that into account, although this basically doesn't change, but in nature your potentials are not weak. They're actually quite strong. The atomic potentials behave like 1/r. Strong potentials. So this kind of simple odd number of free electrons is a metal. Even number of electrons is an insulator is not exactly true. There's a lot of cases where it's not, but it depends on the form of you. But the idea that if your Fermi energy is sitting in a band, it's a metal. Outside, in a gap, it's an insulator. That's correct. Right. Now, okay, we have conductors. We have insulators. What are semiconductors? Hand waving. Semiconductors is a human definition. What do I mean by a human definition?
It's artificial.
No, it's not artificial. They exist in nature everywhere. But a semiconductor is an insulator. Just if we are taking the definition of a conductor where we have an infinitesimal, we're applying an infinitesimal electric field or potential at 0 temperature, all semiconductors are just insulators.
So it has to be with the band, with the size of the band.
So it has a band and the Fermi energy sits in the band. Okay, so why do we insist to call them semiconductors and not insulators? Because we as humans live in an environment which is not 0 temperature. We're living in an environment where we're living around 300 K. So if the size of the gap is of order or smaller than 300 K, we have thermal fluctuations that move electrons from here to here. So we have, if the gap is small, we have a considerable population of electrons, not at the Fermi energy, but above it. And these can carry current. And we'll go through in details over these properties because they are very important for technology. But that's why we call it semiconductor. It's not a real conductor, it's actually an insulator. But at room temperature can behave as a conductor just because the thermal fluctuations send enough electrons into the conduction band, into the band where they can conduct. We'll see another trick that has to do with impurities, where even in 0 temperature we can get some of the electrons into the conduction band, and that will have to do with the fact that we can get charge carriers that are not negative but positive, or create holes in the valence band, the lower band. But at the moment we have only insulators and conductors, and whatever we call semiconductors, that's just our prerogative, just a name that we gave. One thing that you can start to understand, why are semiconductors such good thermometers? You know that any electronic thermometer works with semiconductors.
Because if you have enough temperature, the current will be higher.
Even more, they're very sensitive to. What do we remember from population of states as function of temperature? Think about the Boltzmann distribution. They change exponentially. So a small change. What do you want from a thermometer? Well, you can put your hand and say it's hot, it's cold, but you can't say it's 37.5 or 37.2. There you'll probably be wrong. But the semiconductor, even a change of a tenth of a degree changes the current significantly, and therefore you can measure it. Another game that you play with semiconductors. Next time you're going into an elevator, Why doesn't it close on you? Or hopefully it doesn't close on you. Yeah, it's a sensor, but what does that, that's giving a name to the operation. But what does it do physically?
We are blocking the...
You're blocking photons from reaching a semiconductor. And why does the semiconductor care about these photons? Because these photons can kick it from the insulating state into the conduction band and start to carry current. So, as long as I have my light source and nothing is blocking it in the way to the sensor, to the semiconductor, I will have current. I have current, I'm allowed to close the door. Someone sits or stands and blocks the photons from reaching the semiconductor. No electrons, no current, don't close the door.
But what if you stand there and you use a strong light to shine on the sensor? This would provide enough photons to the sensor.
So that's how to circumvent the sensor. And well, if you're in there, I wouldn't recommend it. Most of these, well, they have to have some wavelengths, because otherwise, if they're too weak, they won't make any difference. But
generally, they tend to be using very weak wavelengths anyway. They tend to be infrared.
Right, they're not using something very strong in any case, just because the gap is small for semiconductors. But these types of sensors are not very sensitive. You want something very sensitive to the wavelength? Look at your camera. That's exactly a semiconductor that is very sensitive to the wavelength. That's how you get a CCD camera. But for the dumb sensors that you have in an elevator, it doesn't care much about the wavelength. So yes, if you'll insist on standing in between and putting a light source, it will close on you. Yeah.
So you need also potential, field, and then to shine a light in order to get the electrons to...
No, the potential is built into the semiconductors. That's the gap structure. If I don't have photons reaching it,
I can have a piece of semiconductor on the table, shine a light and current. Well,
just watch. Some of you have calculators or watches that are charged, or the current that they're using come from photoelectric semiconductors. All the industry of
yeah, but it has it's in a loop connected to a battery.
That is for sensors. Yes, you want a small, but you have a situation where you have a photovoltaic diode that creates current. Now, diode I didn't explain, so I won't. But you can actually create a direction where electrons that are moved go only in one direction. That's the whole green energy industry of solar panels is built upon.
But even in solar panels, we saw in the photoelectric effect, for example, you have a voltage.
No. You don't have a voltage, because if you had needed to have a voltage, what happens when you don't have a power source? There you have a breakage of symmetry, which is basically a diode effect. What is a diode? we are jumping forward to but in very simplistic terms.
An NP junction.
That's how you build it. But
It's a resistor that allows current in one way and forbids in another.
exactly, it breaks symmetry. You put your voltage in one direction, it goes. You put the voltage in the opposite direction, no current. What breaks symmetry? We'll see. It's the structure of NP junction, but since I didn't explain what is N, what is P, I need to explain what are impurities in order to do it. All that, so I can't do it at the moment, but you see that you can break mirror symmetry, parity basically. And that's the point. You put in a photon, it can move an electron only in one direction and not in the other direction. What does it mean? Something moves only in one direction and not in the other direction, you have current.
Assuming we use something like the trick symmetry of the momentum, i.e. energy of one direction and the other direction.
It has to deal with. Okay, I don't want to give you pieces that will sit wrong, and we'll do it in an organized manner from the beginning. First of all, what an impurity does. What's the difference between a P and N material, and what happens when you take a P and N material and put them together. The point is that all this was discovered empirically 20 or 30 years before. Any one of you played with radios?
That was a couple of generations before us.
Yeah, that's in the 20s and 30s, any kid with technical inclination would have played with some kind of ham radio. With
60s,
even in the 60s, I still played somewhere at the tail of it. But nowadays, no one plays. But actually, you can get a radio receiver, meaning you can hear radio without having a battery. And that is the point is you take a naturally occurring semiconductor with impurities. You have to play around and find some point where you can get this P or N junction. And then the electromagnetic waves move only in one direction and not the other. You get a current that you can actually listen to without a battery at all.
Oh, that's what the Soviet spy did in America, I remember. They did that in ambassadors.
Well, that any kid would have bought a crystal of germanium, usually don't know why not silicon, probably it occurred, and play around with a metal wire that is connected to an earplug and string an antenna, a metallic wire of a few meters, and he could listen to radio without buying a whole apparatus. Would have been a weak signal, and you couldn't put it on a speaker because not enough current. If you wanted to move it to a speaker, you had to amplify it. To amplify it, you had to supply current and voltage and all that. But just to hear something, you could do it.
How do you move with frequencies?
You go to different spots. If
Different frequencies will have different resonances.
Right, so you move on to different spots, and let's say in World War II receivers, you would get just different crystals that were tuned to different wavelengths or frequencies, and you would plug them in and they would work. You didn't have just a way to play around with it. Okay, we're too short in time really to have a meaningful presentation of the tight binding solution, so we'll start it in the next lecture.
Thank you.